Welcome everyone. I am Venkatesh from Indian Institute of Science. I will be teaching you the course on Introduction to Lie algebras. So, in this course, we will mainly focus on finite dimensional Lie algebras. In this very first lecture, I will be actually defining the main objects of the course, and then we will see some properties of them, and then I will end with various examples that will be discussed throughout the course. Okay. So, we will always work over complex numbers. So, let us say C denotes the set of all complex numbers. So, we always assume all the vector spaces that are going to be appear in this course are all finite dimensional over these complex numbers unless otherwise specified. Okay. So, all the vector spaces are assumed to be finite dimensional vector spaces over the complex number C. Okay. So, we also use we will fix some notations okay, in order to actually use them. So, let us denote Z by the set of integers and Z plus the set of non-negative integers and n by the set of natural numbers. Okay. So, here are some basic definitions. The very first definition is the product or called multiplication. Okay. So, let us start with a vector space. Let V be a vector space over complex numbers. So, a multiplication or a product is a bilinear map from V cross V to V. So, given two elements x and y in V, so we will have some image inside V. So, it is linear in first coordinate and second coordinate. So, that is called a multiplication or a product. So, once we have this multiplication, okay, so we will be able to actually define what is called algebra. So, those are all very important objects in abstract algebras. Okay. So, let us recall the definition of associative algebra. So, an associative algebra capital A defined over C is a ring, let us say capital A plus and dot. Okay. So, this is the addition plus and this is the multiplication. So, now, so this is a ring. So, we do not assume anything about the commutativity of the ring. Okay. So, it is just a ring. So, we always assume this ring has this multiplicative identity 1, which we denoted by 1a. So, this is the multiplicative identity Since we are talking about associative algebra, we assume this multiplication satisfies associative law. So, what is the meaning of that? If we take 3 elements from capital A, then we must have x composition y composition z is same as x y times z. Okay. So, this is the assumption on the ring structure. Okay. So, now it is called algebra. It is also a vector space, and this vector space structure and the ring structure should have some compatibility condition. Okay. Let us see what it is. So, A is also a vector space. So, this is like first condition. The second condition, so A with the same addition that you have already in the ring structure, the same addition with respect to that and some scalar multiplication which we denoted by dot forms a vector space over these complex numbers. Okay. So, what are all the compatibility conditions? So, the first condition, okay, let me call it 1. The ring addition and the vector space addition, they must coincide. The ring addition and the vector space addition, they must coincide. In other words, so these two additive groups A plus that appear in the ring and A plus that appear in this vector space, they are all same. And the second condition, so this ring structure and the vector space structure should be somewhat, they should interact with each other. So, the following condition must be satisfied with respect to the scalar multiplication and the ring multiplication. Okay. So, the scalar multiplication we denoted by dot and the ring multiplication we denoted by circle. So, with respect to that we have this following condition. So, alpha dot x circle y should be same as alpha dot x circle y and then x circle alpha dot y. So, this should be true for all scalars alpha from C and these vectors x1 xy from capital E. Okay. So, if you have a ring with additional structure vector space structure satisfying this condition, that will be called an associative algebra A over C. Okay. So, by our assumption we assume always this associative algebra contains the multiplicative identity 1. Okay, that is our basic assumption. So, this 1A always is there. So, now we will actually give a very practical example of this associative algebra. Okay. So, somewhat that motivates us to develop our theory. Okay. So, here is the very practical example. So, you choose n from capital N. Okay. So, let n be an natural number. So, then consider this set of all n by n matrices over complex numbers. So, which will be denoted by Mn of C. So, what is this? So, this is set of all matrices. So, maybe I will use a small letter small a, Aij. So, this is n by n matrix. Aij are all coming from C for all I j coming from between 1 to n. So, these set of all n by n matrices over these complex numbers, they have natural matrix addition. Okay. So, the addition you take it to be the matrix addition. and the multiplication you take it to be the matrix multiplication, and the scalar multiplication you take it to be the scalar multiplication of matrices, okay, the scalar multiplication that you already know. So, with respect to this operation, Mn of C forms an associative algebra over C. Of course, the identity matrix, so identity matrix is the multiplicative identity. Okay, this is a very important associative algebra. So, this is also finite dimensional algebra. Okay, we know many things about this algebra. So, for example, the dimension of this algebra is actually n square. Okay. So, the dimension over C of this Mn of C is actually n square, and we also have this very nice basis given by this elementary matrices, okay, which we denoted by Eij. So, what is Eij? So, Eij is the matrix that has entry 1 at ijth position, and all other entries will be 0. Okay. So, this is a matrix where, okay, using again the same notation. Let us say this is ARS, where how this ARS given? ARS equal to 1 if RS is same as Ij, otherwise it is 0. Okay. And it is a simple exercise to see that this Eij, when it varies over 1 to n, form a basis for this Mn of C. Okay. So, here like when we take n equal to 2, we can write down explicitly what are all the bases. For example, you can see that 1 0 0 0 and then 0 1 0 0, 0 1 0 0 and 0 0 0 1. So, there are 4 elements, okay, in each position. Okay. So, this will form a basis for M2 of C. Okay. So, now we are almost ready to define the main objects of our interest called Lie algebras. Okay. So, Lie algebras, they are again algebras, but in very general sense. So, we will see like what does it mean, and they are actually highly non-commutative, non-associative algebras. So, they are not like these associative algebras. Okay. Associative algebras can be highly non-commutative. For example, Mn of C, it is easy to prove when n is greater than or equal to 2, Mn of C is always non-commutative. But these objects, Lie algebras, they are also non-associative. So, they are much more harder to deal with. Okay. But let us first see an example to motivate, so where they actually come from. Okay. So, like I said it in the introduction, they indeed come from the theory of Lie groups. Okay. To understand Lie groups, so you take this linear approximation which are called Lie algebras, and then from algebraic structure of this Lie algebra, somehow you can understand the structure of Lie groups. Okay. This is the theory of Lie groups. But anyway, in this course we will not actually get to see Lie groups. Okay. We will be only focusing on the Lie algebras and the algebraic side. Okay. So, mostly we will deal with algebraic ideas in this course. So, because of that, I would like to actually tell you from the algebraic point of view why these Lie algebras are motivated. For that it is better to see some examples, from that it will be very clear what we are actually really interested in. So, let us take this associative algebra that we have seen, so which is just Mn of C. Okay. So, what we are interested in, actually if you actually just ask this basic question, because this is highly non-commutative, okay, I will leave it as exercise. So, prove that M1 of C is non-commutative if n greater than or equal to 2. Okay. So, because this associative algebra is actually non-commutative algebra over C, okay, one can ask this following question: how far it is being away from the commutative. Okay. So, then naturally what one does, so if you have seen finite group theory, in finite group theory, so you define what is called this commutator group, and then you try to understand the like how big or how small this commutator group. In some sense, by computing the size of this commutator group tells you that how far that given group is stay away from being abelian group. Okay. So, similar to this Mn of C, if you are interested in understanding how far it is actually stay away from being commutative algebra. Okay. So, then we need to understand the commutator structure. Okay. So, that is why what we do, we actually define what is called this commutator bracket, and then that commutator bracket is actually going to give some extra algebraic structure on this Mn of C. By understanding this Mn of C with that commutator bracket, whatever the structure that is going to give that algebraic structure. So, that in some sense will determine how far it is being away from commutative algebra. Okay. So, that is a basic idea. Okay. So, define this commutator bracket like bracket small a comma b to be a b minus b a. Okay. So, this is defined for all a b in Mn of C, and this is actually it is easy to see, it is a bilinear map from Mn of C cross Mn of C to Mn of C. There is no issue with that. I will leave it as exercise. So, just check bracket that we defined using the above formula is actually a bilinear map. Over this complex numbers. So, now what is our actually goal? So, this Mn of C, if I take this bracket, so this is actually a new product that we have defined on this Mn of C. So, this is a new product is defined using the old product, which is the matrix multiplication. You can see that if two matrices commute, if and only if this bracket will be 0. Okay. So, somewhat it is actually closely related to two matrices being commutative or not. Okay. So, that is what this bracket of AB detects. So, in some sense, if this new product defines some algebraic structure on this, and then if we actually could understand what is that algebraic structure, so then we could actually somewhat deduct Mn of C be like how far it is being away from commutative and so on. Okay. So, that is a like very like vague goal. Okay. But for that we need to understand what this commutator bracket actually, what kind of properties it satisfies. So, we will see there are some basic properties that this commutator bracket satisfies, and then we just take those properties, and then we will use those properties to define our important this algebraic structure called Lie algebras. Okay. So, the very first property is this bracket being linear map over C. Okay. That means you have a product on this space. So, now what is about the properties? The very first property, okay, or the second property is that if you see the bracket of A, that should be 0 for all A in M1 of C. Okay. So, that is easy to see because A commutes with A, that is all. And the third property, which is actually somewhat non trivial. So, this is called Jacobi identity. So, this is very important identity, so that this commutator actually satisfies. So, what it is? It just says if you take 3 elements A, B, C in M and C, then how the products between them are related. So, it's a question that you ask. Okay. If you define a product actually gives what happens between given 2 elements. So, using that, then you can also ask what happens between 3 elements and so on. Okay. So, in associative algebra you have associativity, but here in the Lie algebra you have this Jacobi identity. So, what it says, if I take bracket A, B, C and then you just cyclically permute them and then take sum of these elements. Okay. So, what will happen if you cyclically permute? So, you take A, you take B and then you take C. So, you just permute like this cyclically. So, then the first term corresponds to ABC, then the second term should correspond to BCA and the third term should correspond to CAB. Okay. So, that means, so then you take this what is called this Lie bracket elements, okay, B bracket C A plus C A B. So, this if you take these 3 elements corresponding to the cyclic permutation and add them together, then you should get 0. So, this is what Jacobi identity says. It is actually very important exercise, one should actually do it in their lifetime once at least. Okay. But anyway, I will do it for you, you can just verify this. It is very simple calculation. So, let us verify for the commutator that we have defined. Okay. So, let us calculate these elements and then see what is happening. So, recall what is the commutator? Bracket AB is nothing but AB minus BA, that is what we define for elements of M1 of C. So, then what is A bracket BC? So, how you compute this? First take bracket of BC, which is BC minus CB, then take the bracket with A. So, then what it is? It is A times BC minus CB minus BC minus CB times A. So, if you just do the calculation, then it just gives ABC is equal to ABC minus ACB minus BCA plus CBA. Okay. So, now if you just use this first cyclic permutation, then it is just you just do it on the left side, on the right side, then what you get? You get BCA minus BAC minus CAB plus ACB. Okay. Similarly, if you take C and then AB, so then you get CAB minus CBA minus ABC plus BAC. Okay. So, this is your the first term, this is your second term, this is your third term. So, now if you sum them 1 plus 2 plus 3, so you can see what you get. So, let us use different colors to cancel the terms. Okay. So, if you take this green, this ABC gets cancelled with this ABC, and then this ACB gets cancelled with this ACB, and this BCA gets cancelled with this BCA, and this CBA gets cancelled with this CBA, and then CAB gets cancelled with this, and BAC cancels with this BAC. Okay. So, that means if you add them you get 0. Okay. So, this is a very important identity called Jacob identity that is satisfied by the commutator bracket that we have defined on this Mn of C. Okay. So, the bracket, that the commutator bracket that we have defined on this Mn of C, it is not only just a bilinear form, bilinear map from Mn of C cross Mn of C to Mn of C. So, that also satisfies these two conditions. Okay. But let us look at this first condition, that the second condition, I called it L2. This L2, if you just closely look at it, so this is also equivalent to the following condition. Okay. So, the condition L2, so this is bracket AA being 0 for all A in Mn of C. So, this is, if you think about it, for example, if you calculate this A plus B, so then what happens? So, this must be 0 because they are same elements, but if you use linearity on each coordinate, then what you get? You get this is AA plus AB plus BA plus BB. But note that AA is 0 and then BB is 0. So, you get bracket AB plus bracket BA. So, that means the condition bracket AA equal to 0 implies the bracket AB is being minus BA for all AB in Mn of C. So, that means the condition L2 is equivalent to this L2 dash, which says bracket AB is same as minus BA for all AB in Mn of C. Okay. And conversely, from L2 dash it is easy to go to L2. For example, you can take B equal to A, then bracket AA will be equal to minus bracket AA. So, that means 2 bracket AA will be 0, that will imply bracket AA is 0. Okay. So, that proves this L2 is equivalent to L2 dash. Okay. Of course, you need this field to have characteristic 0, we are working over complex numbers. So, there is no issue with this. So, because of this condition L2 dash, we call this condition as Q symmetric. Okay, because when you take the product and then reverse the product, you are getting minus out. So, this condition is called Q symmetric in mathematics. Okay. So, now we are ready to define our objects of interest by generalizing this example. Okay. So, we define these Lie algebras as follows. Okay. So, here is the definition of Lie algebras. So, what is a Lie algebra? Okay. A Lie algebra, to begin with, it should be a vector space. A Lie algebra. So, we always use these German small letters to denote these Lie algebras. For example, I would prefer to use small g in German. Okay. So, this is, you read it as G, but it is German G to denote Lie algebra. So, this is a Lie algebra. So, first of all, it is a vector space over complex numbers and equipped with this product, okay, which we denoted by bracket, which is a map from G cross G to G. Okay. So, that should satisfy some conditions. What are all the conditions? So, those conditions that we saw earlier. Skew symmetric and this Jacobi identity. So, let me just call that as L1 because this being product is actually natural. So, that should be a bilinear map from G cross G to G. So, we will only call L1 as skew symmetric condition. Okay. So, either I can write XS 0 for all x in G, and I will leave it as exercise. This is equivalent to the condition that we wrote for skew symmetric, that is being bracket x y equal to minus y x for all x y in G. Okay. So, this is called skew symmetric. So, the second condition we call it Jacobi identity. So, that is again given 3 elements, how they are related by the products of 3 elements. So, if you take product y z and then with x, then take z x and then with y, and then take x y and then with z. So, then the sum of these products should be equal to 0, and this should be true for all x y z in G. Okay. So, this is what we call Lie algebra, and as I said earlier, so M1 of C is a very important example, and we will actually see later all other examples will appear as subalgebra of that M1 of C. Okay. So, just to emphasize the Lie algebra structure on M1 of C, so what we do, we use this new notation. Okay. So, we call it GLNC. What is GLNC? It is that Lie algebra M1 of C with the commutator Lie bracket. Okay. So, this is called in literature the general linear Lie algebra, okay, over C. Now, it is not hard to see if you take any associative subalgebra of M1 of C. Okay. So, let us take A being associative subalgebra. So, then A can be made into Lie algebra using the same commutator, using the commutator bracket. Okay. So, you take same this bracket A B minus B A, so that is going to give you Lie algebra structure on this associative subalgebra capital A. Okay. Again, to emphasize this Lie algebra structure on this capital A, we denote bracket A by that Lie algebra. Okay. Again, whenever I use this bracket comma bracket, that means it is an actual commutator bracket. So, this is actual commutator bracket comes from associative algebra. For general abstract Lie algebra bracket or the Lie bracket, I use without comma, like here. Okay, I will use without comma. Okay, so I will stop here. We will see more examples in the next lecture. Okay, I will also prove some of the basic properties of Lie algebras in the next lecture. Thank you.